Hi guys, good afternoon, and today we might finish off this whole chapter on reaction kinetics. Now, so far, what we have done is we have actually deduced. Okay, we have deduced. Okay, the rate equation. Remember, the rate equation is deduced from experimental data. Okay. And experimental data, okay, the raw data comes from the change of concentration of reactants and time. So from this raw, this only one, of course, you can get change of products concentration, but mainly it's change of reactants concentration. Okay, from the raw values here, you plot a graph. You plot graph. Before that, okay, I forgot to tell you that, see, in the last part of here, they say, devise a suitable experimental technique for studying the rate of reaction from given information. Here, I told you that two is it. One is titrimetric. Okay, where you titrate a certain substance that can be titrated. Normally, of course, in this case, it's your iodine. It's quite common. Second one, of course, is colorimetric. That means you have to use a colorimeter. And one of the reagents or products, reagents or products is what? Is color. Okay, I've done it with you already. So, okay. So from this experimental results, you plot a graph. The first graph that is important, of course, is the concentration of reagents versus time. Here, there are three kinds of graph. Okay, three kinds of graph. Like I'm going to show you here, so save time. I'm going to finish everything today. Okay, there are three kinds of graph. You can see here. All right. Okay, here. Remember? All right. Now this is the concentration here, moles per dm cube of reactants. And this is the time. Of course, this is where you start, and of course, there's the first graph is straight line, where like for example, iodine and propanol acid. There are two graphs which is the curve. This is actually there's two and there's three here. So remember, we are only asked to determine order, okay, of 0, 1, and 2. Okay, no others. So it's three graphs here. The straight line is of course 0 order. Okay, why? Which means there's only one 0 means what? Means rate is equals to k, and your x here is power 0. That means the rate is a constant. And how do you determine the rate? The slope, isn't it? Right? Theta. And there's only one slope for whatever concentration or initial concentration of your reagents are. So it doesn't matter what its axis. Can be here, or here, or here, right? It will always be a constant. Why? Whatever number here, the power of 0 is 1, isn't it? But 2, the power of 0 is 1. 100, the power of 0 is also 1. So rate is constant. That's why this is a straight line graph. But the curve is hard to determine the second or the first order. So if it's a first order, you can determine straight away from what they call if it's first order. So normally in most of your question, you determine by half-life. Okay, you need to find the two half-lives to make sure they're the same, right? Because half-life is the same for first order. Then you can conclude it's a first order. But of course, you can plot a subsequent graph of rate of reaction versus concentration, which means you take, for example, it's a straight line here, right? So in this case here, for whatever concentration here, right, the rate here always remains the same. So this is 0 order. Okay. For first order, the green line is this one here, right? That means as you increase the concentration by 2, rate increase by 2. By 3, 3, 4 and 4 and 5 and 5. That means it's like y equals to mx. Okay, so it's power 1 here. So increase by 1, here is y is 1. Increase by 2, here increase by 2. Okay, and this exponential graph here is second order, this first order, this second order, right? Where this is y equals to mx squared, where it's exponential. It increases by 2, right? If it's y equals to here, if x increases by 2, so y equals to, if m is 2, this is 4. If by 3, then if it's 3 square here, it's by 9. Okay, we'll see that afterwards. Okay, so far we have done this. I told you also we can also find another way, which is quite common, to convert all this data into a table. I call it the model of tables. You can see here, right here. Okay, so like experiment number. Normally don't give so many experiments. Just most 2 or 3 only. Okay, then you have to derive from there. So there's always initial concentration. Again, why initial concentration? Because you start with this, you know it, you prepare it. Okay, initial, and then the initial rate. So like here, they give, there are 6 experiments here. Okay, actually need these 2 to compare. These 2, now this is the same, right now. So when here you increase by 100, now this reaction is for this one here, H2 plus NO. Okay, so this is a reaction here. So if I keep the concentration of NO constant, I increase hydrogen by 2. See, the rate increased by how much? This times 2, rate increased by 2. Same as it. So that means it's first order. With respect to this one here, with respect to H2 is first order. Okay. Now then I keep this one constant. So all this are constant. Okay. So I got 3 experiments here, 2 experiments to do. So I increase this by 2, times 2, is it? And how much increase by? 4 times. 0.5 times 4 is equals to 2.0, isn't it? See? If I increase from here to here by 3 times, here to here increase by 9 times. Right? 9 times 5 is 4.5, isn't it? 0.5 here. So, of course, then this is y equals to mx squared. So this is second order. So here be, with respect to this one, is second order. See how? Okay? This actually came out in your past question, no, son? I mean, but it's very simple. Just use it in the graph, in the mathematical way. Okay. So now, of course, you can argue like this: increase by 2, concentration increase by 2, then increase by 2, concentration increase by 3. So 2 increase by 4, increase by 3, increase by 9. Or you can do, like I told you, the ratio way. Okay, the ratio is by ratio. See, in exams they say that or by ratios, See, example ratio. So here they allow, because it's mathematics. Example ratio. Okay, so you can use ratios to prove it, which is easier mathematically. I think if you can't express them in good English, you must use ratio. Okay, but here I compare rate 1 and rate 2. Okay, 1 and 2. So these 2 are same or not? Okay, they will cancel off. The K will cancel off because the rate constant is dependent on the type of reaction and also the temperature. Since both of them are the same, you can cancel off. So this is 1 and 2 here, and 3 and 6 here. You can see here. Okay, so this cancels off 3 and 6 here. This cancels off, and of course you can see here. So 3 over 6 is 1.5. Here's 1.5 B. So B must equal to 1. So it's first order with respect to H2. And of course, the second one is the same here. Use rate 4 and 5. Why 4 and 5? 4 and 6 also can. 4 and 5, right? Because it's the same, isn't it? So this get cancelled off. So this ratio here and this ratio here. Okay, right? So you can see here, right? So 0.5, 2 here, 1, 2 here. This one can cancel off. So this one is 1 over 4 from here to here, right? This 1/2. So 1/2 and power a equals to 1 over 4. Of course, a must equal to 2, isn't it? Right? Mathematics. So it's second order. Okay. So here you can see also I told you how to make, you can use any of those experiments to calculate your K. Right? Use the rate given. These 2 you already found from the order here, and just find K. Of course, K I told you is the units we did last week, or the other day. Okay. Right? So now Now let's look at some of these questions here. They talk about using the table, right? We're going to see a couple of them, and you can see what I'm trying to say. Very simple. It's all mathematics, and it's simple mathematics. Okay, 56, the first one here. Now, okay, order fraction definition I told you already. Is the powers or the exponent or the indices raised to a certain level but of the concentration of the reactants in a rate equation. Okay, okay. From here you can see very simple. Here, see, not here. Yeah, the power index exponent to which a concentration term is raised in a rate equation. Okay, yeah. Or you can use this equation here. Okay, done this already. So I'm just going through what we did. Now here is the first example. Cyanohydrins can be made by reacting ketones or aldehydes, for the matter, with an acidified solution of sodium cyanide. Okay, right? It's two here. So this is a cyanohydrin, right? It's a nucleophile substitution, and we did this in your AS. I show you here. Right? Remember, this is AS, right? Mechanism is two steps. One step. Let me put this up. So it's important later you find that step 1 and step 2. After you find it's very important to know the mechanism. Okay, no? Right? Now mine first. Okay, so here the first of course the cyanide I will attack. Well, this is not too good. Attack here. Here, move over here. Right? So the negative charge is here, and then attack the H plus here. Okay. So this is the mechanism you learned in your AS. Now, how do you determine now the rate law? Okay, now I did this one over here, so it's easy for me to write. Okay, let's go up here. I did all here, so it's easy for me to say. Okay, so say it here. I can put the general equation here, right? Where rate is equal to K, rate constant. Now there are three reagents here. Propanol, H plus, and your cyanide. Okay, so put A, the power here, B, and C here. I want to determine A, B, and C, which is called the what? Orders. Okay, so given this data here, so how do I use the data? Very simple. You look at this one and say, well, which to compare with? Very simple. The three of them look for any similarities, any same. Those who are same can be cancelled off. Now 1 and 3. Okay, 1 and 3. This and this is same, right? Okay, cyanide, this and this is same. That means now I'm changing only this and this, right? So now the numbers here 0.06 to 0.05 hard to visualize how much is a change. It's times 2, times 4, times whatever, and it's very hard. So the best, of course, is sometimes it's quite simple. In this case, it's quite simple because see the rate didn't change, right? Same. That means if I change the constant H plus here, the rate didn't change means it must be 0, you know. See? So I must say the rationale. Rate change 1 and 2, experiment 1 and 2, H plus change from this and this, right? Change from 0.06 to 0.05. The rate remains unchanged. That means H plus is 0 order. You must say this because they ask you for the rationale. See now here. Okay. Here. Okay. Use the table. They didn't say here, but later they say they ask you for rationale. Okay. Let's do the next one. The next one is here. Okay. Subsequently, of course, I can compare 2 and 3. So if I compare 1 and 2, I'm looking for my H plus. What is the order here? Okay. For 2 and 3, I see, well, this and this are the same. Right? Right? This and this are the same. That means what is changing, of course, is my cyanide. Okay. So from 1 and sorry. Oh, 1 and I still forgot. Okay, 1 and 2, sorry. 1 and 2. Mr. Lai is okay, never mind. Okay, 2 and 3 again. 2 and 3, sorry. 2 and 3, okay? So this one is changing here from here. Okay? Right? That means my cyanide here. Right? 2 and 3, correct? 2 and 3. Okay, here's changing. That means I increase, here increase now. So 0.05 to 0.0 is very hard to know the amount. So I put it in this way. Okay, so rate 2 over rate 3, I use the whole equation here. I just put the concentration here. Remember, the propanol can be cancelled off, so also can be K. Okay, K is same. so can be cancelled off. So what left behind is of course the concentration of what? Of your cyanide here. So, okay, which is equals to the rate. This one here is this one here. This bottom one is this one here. Okay, 2 and 3. Okay, so right. Okay, so now here I equate it out. So here this part here is this part here. Okay, it's equals to 0.823. So I find calculator is the same. So here C must be 1. Okay, okay, C is 1. So it's first order respect to your cyanide. Now to find the last one, which is the propanol. So I see what can be compared. So I can see that this one here, I put a red color, so easy for you to see. Red color. Green color. Okay. See, I put here 2 and 4. 2 and 4. Why 2 and 4? See? So it's not the same as, doesn't work again. We'll do something. Okay, should work. Okay, 2 and 4. See, this is same as it. Cyanide. This is same as it. So correct. So it's 2. Okay. So all these get cancelled off. So I just put straight away. Okay, rate 2 and rate 4. Rate 2 and rate 4. Rate 2 is what? This one here. 4 is here and here. So then the concentration is this one here, which is this one here, and this one here, which is this one here. Okay, K get cancelled off, same. So put the A here, the powers. So it's 0.8333 here over this one here. Right? So if I do the mathematics here, okay, all right, it's this one here. So same. So again, first order. Therefore, I can put the rate. It's equals to K concentration of what? Propanol power 1, right? Cyanide power 1, the cross H plus with power 0. Okay, so easy is it? So now let's look at another example. Okay, now here, same thing. Okay, again, this is the equation here. We did this earlier, but it's half here now. That was 2NO plus O2. Doesn't matter. So this will be your rate law. Okay, every reagent must be included here. Just find the A and the B here. Yes. So now this is the general rate law as I put down here. So rate 1 or rate 2, you compare 1 and 2. Why 1 and 2? Because this is the same. It's the same. So I need this one can be compared to. Okay. Initial rate is this one here. Okay, 1 over 2, you know, okay, 0.02 over 0.03, and the concentration is this one here on top, is at the bottom here. So again, I put the maths down here. Again, this is 0.667B, and it's the same as here, so it must be first order. Okay, second one, compare, I want to find the order respect to NO. So now this and this is the same, so these two, and these two, okay, same thing here, rate 2, rate 3, this is the rate 2, rate 3, the initial rates, right? And it's the concentration, 0.005 here, here, and 0.01 here, here. Okay, A is a power. Okay, so I put it equal, I find, oh, okay, 0.05A, 0.02, of course, means that this is 2 lah, because 0.5 times 0.5 is what? 25, 0.2, that means second order. Okay, of course, in this case, you report your rate equation. Rate is equal to what? K concentration of NO is 2 and your O2 is 1. Simple, isn't it? Right? Okay, quickly. Now here again, right? You can see here. Okay, now this is a general rate law. I go to law of the examples. Okay. Now here you can see I can compare this 1 and 2 because this is same, right? Now, so this and this can be compared, right? Like here, rate 1, rate 2, 1, right? And rate down here, this get cancelled off, and 0.02 or 0.3, right? So give 2, okay. But then for fin acyl chloride here, there's nothing here which is same, you know, right? See. Sorry, for your OH minus, right? See, Nothing here is same, all different. So I can still do it. I still use the same equation, but by introduce this value, I put 2 and 3. Okay, 2 and 3. Right, put inside here. All I do is I must have a different OH minus. So I can use the 1 and 2. Okay, so I use one here, 0.03. I know the power is 1 now. Okay, because I did here. So I use what is here into here. Okay, so I use this one, even though it's not the same, I can't cancel off, it's okay. I put the powers 1 and powers 1 here. See now? So I got this one here, 0.01, 0.1, 0.2 here, B here, equals to 1.5 over 2.5 here. Right? So I put this one and I invert, bring this down here, bring this up, cross multiply. Okay, I can solve for my B. Okay, so B is 1. Okay, all right. So I'm trying to hurry. Now, here, of course, same idea, right? Okay, so remember, I don't have to give everything like in order, you can cancel off. Sometimes you don't have to, you just substitute whatever's known first. This is a generate law. Okay, you got 3 reagents here. Ethanol, methanol, and your H+. Remember, catalyst must also be put inside. Now, okay, this is a red law here. A, B, C is what you need to determine. Now, 1 and 2, of course, you can see that these two are the same. These two are the same, so these two are different. So I can put inside here and find my order. Okay, you can go and look at it. Okay, quite simple. Okay, this can see here, right? 0.2 here, 0.25 at the bottom here. Okay, power A, and this first rate, second rate. Okay, you can solve it out. 0.8, 0.8, so 1, first order. Okay, and 2 and 3, of course, 2 and 3, you can see that these two are the same. These two are the same, so you can find for your change your order with respect to your methanol. Okay, same thing here, substitute inside here, first order. Okay, now the third one, right? The third one here, I will say here, say you cannot compare. There's no same, only this one is the same. But it's okay. I can use this one here because what I already determined. I can find this one here because I already determined for my propanol, right? So propanol here, I can use it here, right? So this can cancel off. So propanol here, 0.25, I put power 1 here, 0.2 power 1 here. So I can still solve the problem here, okay? Right? Okay, so you can get the whole thing here again. Now, next one here. Now, this is a complex equation here which you learn in your chemistry. Now, look at it carefully. Now, this is by power observation. Now, this is your ruthenium, well, chloride, whatever this equals, okay? Right here, here, and here. So the following table shows the initial rate. Right, initial rate, again, all this is initial concentration. Why? Because you prepare them, you know the actual amount. Okay? Now, here you can see that none of them here are same for you to cancel off. So you must use your observation, your power observation. Now, look at here. From here to here, from 1 and 3, you know, it's times 2, isn't it? Now, look at the rate. It's also times 2. They will give you something simple, very easy to do. Otherwise, you cannot, you know, to put in the ratio is very hard because this can be variable. So you can see times 2 times 2, which means if it's times 2 times 2 means like this one must be power 1, is not. See? So I put down here concentration of your ruthenium complex increased by 2. The rate also increased by 2. Therefore, first of all, that's all you're gonna say. Okay? Right? Even though the concentration of CO increases 0.17 to 2.7, it does not affect it. Okay? I can check it by doing 1 and 2. Okay? You can check it if you want to lah. In the exams, you don't bother one. Okay? You compare rate 1 and 2, 1 and 2 here. So you put 1 here, 1 here, that means the power, see, if you put like that here, the rate law, right? Okay, your ruthenium fella here, power 1, and your CO power 0 here. Rate 1 over rate 2. Okay, ruthenium, this 1 and this 1, this ruthenium something, power 1, this 2 here, CO power 2. Okay, this can cancel, isn't it? Right? So you can see that they will be the same, see now, so I did here, right? Same. Okay, about the same now. Okay, sorry, this is something wrong with this 0.697. Okay, so another one. Now this one is, earlier this is in terms of concentration. Now this is in terms of atmosphere. The concentration is in terms of atmosphere. So it's like the rate is atmosphere per second. Normally it's moles per dm cube per second. So remember, very important, later because they will check you on the K, okay, the units of K. So same thing here, right? 1 and 2 is the same, this one change, okay, decrease by 2. You can go back also, increase by 2. Here also increase by what? By 4. So 6 times 4, right? So you can do it by this way. Okay, 1 and 2, change the partial pressure. Okay, why partial pressure? Because it's a mixture of gases in it. Okay, you can see over here, you can use one here, and this one over here. Okay, so this one is on top here, concentration, partial pressure A, and the bottom here. Okay, and you can solve. Is A equal to 2 here because it's 2 power A, 4 is so it's second order. Same thing here. Okay, so 1 and 3 will give you for hydrogen. Okay, hydrogen here 1 and 2. Why? Okay, 1 and 2. Sorry, 1 and 3. Okay, these two are the same. Okay, so from here to here, or from here to here, you can. Here to here is decreased by 2. Here to here is increased by 2. Both same. You can use either way. Okay, the ratio is the same there. Right? Again here. Next one. This done already. It's a repeat. Okay. Now this one after you see on mechanism, this one came out in this form. Okay. The whole reaction is of course, well, you can see later is H plus and Br minus. Okay, and this one here. Well, I'll give it to you. Okay. Where is it? They're here. No. It's right near the end. Let me see. I put down here the page 89. Easier for us. 89. Okay. Right. This one they didn't give you here. Okay. That's enough. They give you bromate. They give you bromide ions. That's a H plus. And they ask you for the equation. No. Very naughty first. Right. Okay. Again here. Okay. And that's it. So the 3. They ask you for an equation. It's tricky for us. After you see how we can balance, okay. So it's good to know lots of examples. Okay, now let's look at this one here in the different form here. Very simple. Now this is the general equation. I don't know A, B, and C. Okay, now these are the 3 reactants here. Because they tell you, okay, they tell you. See, bromide, and acid H plus. They tell you here, bromide H plus. You need to know this bromide. No, in fact, you learn it when you go to inorganic chemistry. Okay, so the first, of course, is look for 1 and 2. 1 and 2. I put here this is same as this. So I can find for H plus now. Okay, same thing here. H plus. Okay, first one here. So I found H plus here is second order. Okay, now 0.5 A. Okay, second order. Second one, 1 and 3. Why 1 and 3? 1 and 3. I don't know why it keeps on bugging me. Let's do it again. Okay, blue color. Okay, 1 and 3. 1 and 3. Same. No. So these two are different. So compare these two. Same thing here. Okay. So here is 0.02 on top here. 0.08 here. Right. Power of B. And of course here is 2.64 power of here. And the bottom here. Okay. So I get this is the answer. So B must be equal to 1 first order. See now. Finally, of course, is 1 and 4. Okay, 1 and 4. Why 1 and 4? 1 and 4. Okay, I put red now, better so you can see color. Okay, 1 and 4. 1 and 4. 1. This one is same as this. It's the same as this. So these two are changing here. Okay, so same thing. And this one here I compare. I can find, okay, here. So it's power 1. So this is the rate law. So the more you do, the more easy for you to spot which are the equations to choose. Okay. Now here I didn't bother to do all the things. Just very simple. This one came up before, but it come in half. Okay. Okay, came out in partial pressure. Now, of course, here, right? You can see to compare, which one to compare, NO. There are only two, isn't it? Two things here. So now these two are the same. So to find oxygen, I compare this and this. Times 2, here times 2, isn't it? So easily it's first order. You can talk like that one. You don't have to use the ratio method. You just say increase by 2 times, rate increase by 2 times. Okay, first order. All right, so 2 and 3. 2 and 3. These two are the same. So here, increase by 2 times, here increase by how many times? 4 times now. Yeah. 8.15 times 4 is about 3.32, is it? Something else. This one. Okay, so from here you can find, you can use the ratio method. Now to find this one here, very simple, right? Remember your rate law, K concentration of NO. The power we find is what? 2, isn't it? Okay, O is what? 1. Okay, so you use, of course, to find this initial rate, all you need to find is the K first, right? So to find the K, you substitute anyone, experiment 1 or experiment 2. Okay, just something like here, 4.08 times 10 to the power of -3 equals to K, and here is 0.032 power of 2 and 0.012. Solve for your K. Okay, after finding the K, then use this one here, right, to find this one here. So now the rate for rate 4 is equal to the K times, of course, 0.096 power 2 and 0.036 power 1. Can I find it? Right? Can I find your rate 4, is it? Okay, very simple. This is just mathematics as well. Okay, so same thing here for this equation here, right? These two are the same. You can find the order is one here. These two are the same. You can find the order. Okay, I won't go through that because time is catching up with us. Okay, right? Same thing from here. Again, to find some here, you need to calculate the K first again. Okay, right? You can see here, these two are the same. So here times 2, here is what? Times 2, isn't it? Right? Here is same. Here is times 3. Here you can see is also here to here is also what? Okay, times 6. Okay, times 3 as well. Okay, you can see. Okay, here all right. Last one here. Now here they give you a change of scenery. They give you the rate law. They give you the powers. Is powers 1, powers 2, powers 1 here. Yeah. So from this equation, from this first one, you can calculate the K. Okay, right? You know the rate, you know the concentration, you know the orders. You can calculate your K, right? From there, you can calculate your initial rate. You can calculate this one here. Okay, so all this is mathematics. Okay, I finished about all these rate law things, right? Using the mother of tables or the table of values. Now let's go to the final bit here. All right, final bit here, which is actually mechanism. Okay, which I can finish today. Okay, about half an hour more or so. So here, where is it? Okay, here. Okay, so here for multi-step, now very important to use multi-step here now, because you are going to use elementary step afterwards. Remember, elementary step means one step. Multi-step means many steps. Can be 2, can be 3. Normally 3 or 2 and 3 or 4 sometimes again. Okay, so suggest, they say, or we normally say predict. Okay, predict a mechanism that's consistent with the rate equation and the equation of the overall reaction. Okay, so these two things here. Okay, so rate equation and overall reaction equation. Okay, you can see this how these two tie in together. Okay, okay. Predict the order that was result from a given reaction mechanism, okay, and vice versa. You can see how this whole thing related. Okay, so it's the last part we're going to do here. Now I'm going to show you some example first. Okay, you can see here the examples I've got here. And some of the examples came out for exams now. Okay, so I got from this book. I'm not so smart as to invent my own. Okay, this book is a very good book. It used to be ELBS book. It's a cheap book, but it's because it's so good that people used to use it for A levels long ago. But it was very good, and now they use all these examples for exams. tricky fellas. Okay. Okay, here we are. Now I'm going to use the first one here first, okay? Now, see, the rate of reaction and mechanism. The order of a reaction, order we just determine the order of reaction, okay? From order, of course, we determine the rate law. K, whatever. And here is HBr power A and O2 power B, okay? Now I need to stop for a while here first. Okay, let's start again. All right, now here, now you are normally given the equation. Okay, they ask you to speculate or predict. Okay, the mechanism of the reaction. You cannot prove it, not by anything else. So you need to use, you need to come up with some ideas. Okay, to suggest. Now they say that this is the equation. They give you the equation, right? It's called the overall equation. Remember, this one say overall equation, is it? And this is the the rate law or rate equation. So there are two equations here: overall equation, okay, and the rate equation. Two things you must now use these two things to speculate the mechanism. And this for multi-step, Okay. So now you must understand first thing, of course, sometimes Cambridge does, I think to me like Langgakan plus Toran. Okay, most chemical reaction takes place in a series of multi-steps and and they normally collide two different things to collide. The collision in two, not three, not four. Okay, two will collide two different things, and every step involves only two. Normally, two only. Okay, so this is a normal assumed mechanism. Not three fellas. Two fellas can always meet by chance quite constantly, but three fellas meet at the same time all the time. That's very difficult. Low probability. Okay, now this is the proposed mechanism. Now here we're going backwards. Okay, now the proposed mechanism is that first of all, remember now this one here is HBr, hydrogen bromide. Four of them and four molecules in one molecule. Okay, now five molecules can't meet together at the same time, is it? All the time for every reaction cannot, no. So something must be happening with two meeting each other first. Can be HBr, and O2 and O2 and O2. Okay, these are the possibilities. So they say, well, we found that these two, see, these two are in this is called a rate. That means these two are involved in the slowest step. See, a multi-step means the slowest step will be called the elementary step, and that step, the two regions there will control the rate. For example, you run a 4 by 100 relay. Team A, Team B. Team A got 3 good runners and 1 Chekai runner, 1 very slow runner. Team B got 4 but mediocre runners. And how come Team B always win? Because Team B, all the 4 fellas are okay runners, but Team A, the Chekai runner, the lousy runner, is the slow fella. So they always slow. So the overall rate depends on the slow guy. The slow guy will control the whole race. Same thing here. Right? The slowest step in the mechanism will control the rate. That means here we say that, well, these two fellas are controlling the rate. The power 1 and power 1. Okay? Now, if you find an overall of 2, 1 plus 1 is 2, or not? That means these two will be in the first step normally. This is quite okay. You can come to the conclusion. Okay? That means the first step, these two end is the slowest step. Okay, now here, so I put here HBr plus O2 give you HO. Now this is what? This is intermediate. Intermediate. Okay, it's not a reagent. Okay, intermediate form HBrOO. The second step they propose is HBOR plus another HBr. Why you must put this on? Because at the end when you add it all, you must give you the overall equation. So it has to react with HBr. Okay, to give you H. So this is a reagent, and this HBrO is also another intermediate. Okay, right? And of course, this intermediate now react with HBr, which is a reagent, to give you this is a product. How do you know it's product? You can see from here. See, water and your Br2. See, okay, product. Okay, And of course, since there are 2 moles here, so 1 mole here, the second mole same here, okay? Right? Now you need to put all this down. That means the proposed is 4 steps. Now you must, these 4 steps, when you add them all together, it must give you the overall equation. Overall equation. This is the key. Overall equations now. Okay. So every step here, right, add together will give you the overall equation. So you add here. So now remember, okay, this one cancel this one here. Okay. 2HBRO cancel this 2HBRO. Okay. Right now. Okay. So here you get what? 4 HBr, 1 O2. Give you here 2 moles of water, 2 moles of Br2. Is consistent. They say consistent with the overall equation here. See now? So they must, all the steps here, the multiple add up together must give you the overall equation. Right? This is how you propose it. Okay? So here. Remember, each step involves only 2 moles. Only 2 moles collecting together, not 5 moles. Okay? So this is how you propose it. Okay? Now this is an example. Okay? So there are 4 steps here. And why is it the slowest? Because this one becomes the elementary reaction. Okay? So that means the first step here is slowest. Why? Because these 2 fellows here is found where? It's found in the rate equation. Why? Here, see now. See? Put blue color. See now. Power 1. Power 1. Why power 1? It's 1 more and 1 more here. See now. Okay? So these 2 are involved in the rate equation. Okay? Now, next one here. Now this is the famous reaction, remember the propanol with iodine with your H+. Okay, now this is the rate law that we found, right, from our from your graph and from your table of values. Okay, iodine is 0 order, H+ is 1 order, propanol is 1 order. Now what's the mechanism like? So how many steps you don't learn this, okay, but you should know it. So the first step they say is a slow step. Why? Because why is it slow step? Because these 2 fellows here are involved. So here, these 2 fellows are involved. It means that iodine here is 0 order. It means that it's not involved in the slow, it's involved in the fast step. So 2 fellows here, power 1 + 1 power 2. That means that the first step will be the slow step. This is how you actually can come to the conclusion. It's very simple. I mean, it's take a lot of experience to do it. Okay. So the first thing, of course, is now this one. You say you cannot predict all this one. This is very hard one. They give very simple ones, okay? This will show you how it happens, okay? So these 2 are reagents. These 2 you can see from here, propanol and acid, okay? Now they say that this happens, okay? Of course, this one will, electrophilic addition is it? H+, and of course this one go to here, and this one become positive here. Carbonic ion form. And now this part here by itself, it undergoes what you call a what? Elimination. Sorry, elimination. Sun go down here. Okay, come on here. Okay, and the double bond here, and of course the iodine will add on to here. Okay, so they found that the iodine is one of the fast step, so this one will not control the rate. Okay, so the slow step, which is these two fellows here. That's why these 2 fellows here, right? It appears in your rate log. Right, so if you add them all up, right, it will give you this. One more reaction here. Okay, one more reaction here. Sorry. Okay, the fast step, of course, is when this comes up, when the I and the H comes up. Okay, and gives here. So you add it all up. See, this is an intermediate. It will cancel off with this intermediate here. Okay. Idiot. Okay, this intermediate, the 2I here will cancel off them. Yeah, cancel off. Right? And then this intermediate will cancel off. The intermediates will all be cancelled off. At the end, right? In the end, when you add up all the equations here, you get propanol, acid, right? And what? And iodine, right? And you get what? This one here, this one here, and this one here, which is your equation. See now, okay, right? So you can go and try it yourself because I got no time to waste. Okay, I want to finish off properly. Okay, now this one came up for exams. No, this one I'll show you what's on here. Right, I just told you just now came up for exams. You can see here. Okay, this one here, the last part. Okay, so they do take from this book. Okay, let me show you. So it's good to get more experience. You know, so you'll be caught. But here, because they see here, see here, right? Bromate ions, bromide, you know, bromate ions, and acid. They ask you for the equation, no? They say, oh my goodness. So how to do, man? That's why I say you will go over my notes. Not any book will do that. But of course, I try to expose you to most of this. Okay, now here, see now, see bromate. Hard to remember, man. Bromide and H2. Of course, they tell you that they get bromine and water. So you use the brains a bit, you know, how you're going to get the whole thing. Okay, never mind. Now this one, he say, there are altogether 12 molecules, no, 5, 1, and 6. How can 12 molecules suddenly bang together all the time to give the reaction? It's very low probability, isn't it? So there's a mechanism, right, where every time 2 and 2 will bang together, right? So what are the steps you can get now? First time you can see here, red has got this K, this power 1, bromide ion, bromate is power 1, it's 2. It means there are 4 things involved in the slow step. That means if the 4 involved in the slow step, that means the first step is not the rate determining step. We call it the rate determining step. Okay, slow step is called the rate determining step. That means it's going to be determining step. That means it's going to be, right, the elementary reaction. Okay, elementary reaction. Okay, so now what is the proposed mechanism? Right? Well, they say 5 moles of H plus, 5 moles of Br minus. Okay, now put times out here, give you here. Of course, it means 5 moles here. Okay, HBr. So every time H plus and Br minus will collect. Okay, we've got the 5 here, 6 in it. So 5 of them will react. Yeah. Okay. Now this is an intermediate. Okay. So when this is formed, it will react with this. Okay. Okay. Here's it. Okay. Now this is H plus. This is your reagent. This is your reagent. To form HBrO3, this is an intermediate. How do you know this? You don't know. This is what they suggest. Okay. You don't know one. Okay. I'm telling you this is an example here. These 2 are intermediates. So how will this react? Now they propose the HBr, which is intermediate here, from here, okay, it's an intermediate, will react with here, the intermediate, to form another intermediate, HBrO. Another intermediate, okay, so there are a lot of intermediates here. There are 4 types of intermediate, HBr, HOBr3, HOB, HOBr2, okay? So then later, of course, this intermediate, this one here, okay, react with your first intermediate HBr to form HBrO. It means here 1 and here is 2, or 3, isn't it? Right? So 3 here will be here. Okay, 3 here. So 3 here will react with the rest of the, see, 2 of HBr here, so you have 5 here, 5 here, you know. So 3 left, 3 here to give you your water and your Br2. Now, I know it's a very complex mechanism. You cannot do this one. Okay, they will have to give you the steps. Okay, now remember this will be correct if you add up all. They will ask you later. You see the question. They ask you all. Okay, now we add them up here. Here got 5 HBr. 5 cancel off with this 5. No, 1, no, 5. Okay, so here's 1 HBrO3 cancel off with one here. Yes, so here got 1. So now here got 1 HBrO3 together, cancel this 3. Here HBrO2 cancel this one here. So what's left behind is 5H plus plus 1H plus 6H plus. Okay, right here got 5 Br minus, 5 Br minus, 1 bromate 1 here. Okay, now here must give you 3 water, 3 Br2. When you add up all of this, you must give you the overall equation. Remember this overall equation. That's why you can see this page 40. You can see here in the syllabus, they actually tell you that. Okay, see now, right? and the equation for the overall reaction. See, you must know Cambridge is not stupid, no, quite smart. They put it here, but then how you apply it, I can see now, okay, from the mechanism reaction. So I told you there are two equations. One is the rate equation, one is the overall equation, okay. So just a mechanism. That means the mechanism must come from two equations. One, I told you, is the rate equation. Second one is what? Overall equation. So two equations I require, okay. So you can see down here, page 40. Yeah. So you must understand how Cambridge word the words here. Okay. So you must know the examples here. All right. Okay. So this step. So now, which step is the slowest? You say, well, okay. So they tell you that this is the slowest step. They tell you, otherwise it's very hard to tell. Okay, that means the slowest step involve 3. Okay, I'm going to put in red pen so you can see easier. I have about 10 more minutes. Okay, okay, right here. We can do it. Now, this step, they say it's a slow step. Okay, slow. That means it's called the rate determining step. Or they call it what? Elementary reaction here. Okay, so involve these two. So that means I can write here the rate, equals to here's power 1. So you can see here power 1 here. Okay, HBr power 1. HBrO3 power 1. Okay, but these two are not reagents, see? So remember, rate here must be proportional to the reagent. So how to convert this? Where does this come from? Came from here. See now? So convert this going backwards here. It came from H plus and Br minus 1. Since 1, you use only 1. See? H1 here and here. So this is converted to here. These two. Okay? Right? Now this one is also intermediate. HBrO3. Where it come from? This one here. I'm going to use a green pen so you can see easier. Green. Okay? Now, this fellow here is an intermediate, which is this fellow here. Okay? In terms of reagents, it comes from these two. These two are the reagents. It means I must change this now. So it's H plus power 1 and BrO3 power 1. So, okay, now so these are now all these are all reactants now. So there are 2 H plus here, so I put H plus power 2. Br 1 minus here, minus is 1 power 1 here, and Br, okay, now so this is the final rate law. Got it? Go back and think about it. I don't have time to go over again and again, okay? This first playing me up all the time. Okay, so this is the answer here. Okay, right, now let's look at some examples. Now it's so interesting. Examples, okay? So we look at page 59, right? Quickly, okay, now this is a very good example, okay? Coming from the last one here. Okay, in 9th century and blah 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 and blah 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 blah. Now this is the reaction here. Hydrogen peroxide plus I minus H plus here give you this iodine. You do this called the iodine clock, iodine clock reaction. Iodine clock means the blue. I call the blue ghost. Done before in the lab. Okay, there are altogether 5 molecules here, 5 moles here. 1 is 2 is 2 5. So they cannot 5 together. So every step is 2 except this one here. I don't know how they come up with this one, but don't care. Okay. Now, so step 1, 2, and 3. Now they didn't tell you. They always propose the mechanism. You have to consider which is the one. Okay. Now they tell you the general form of the rate equation is this one here. It's true then, right? H2O is A, I minus B. Okay, see now. Suggest how the appearance of solution might change. Okay, of course, turn to iodine, become yellow color. If you put starch inside, it will turn blue. Okay, so it's called the iodine clock, or the blue ghost, I call it. Something come, ram, the blue color come out. Okay, all right, now here, suggest the values for the orders A, B, and C in the rate equation, right? In the rate equation for each of the following cases. Now, if step 1 is the slowest overall, understand step 1. If step 1 is the slowest, okay, step 1, okay. Remember, look carefully, step 1. These two are these two. If this is a slower step, slower step means a slower step, but it says this is a slower step now. That means it's what? This is the rate determining step. Okay, don't say elementary step. This is the correct word. Okay, slower step. That means now these two are reagents. Okay, so of course is proportional to this one here. Okay, that means these two are reagents. The other reagent is your H plus. It's not in here. That means this must be 0. This must be 1 and 1. Okay, that's why here. This will be 1 and 1 is 0. Okay, step 2 is the slowest. Step 2. Okay, step 2 is slowest. That means it's the slowest step. It's the slowest step. Not this one here. Okay, second one I put red color. Okay, red color. This is the slowest step. Slowest now. That means, okay, now this is a reagent, but this is not reagent. So, but I put it down first, okay? So it is equals to IO minus power 1 and H plus. So now this one here, I must change it to reagents. Where does this come from? It came from here. It came from these two reagents. So I must now convert IO minus to H2O2 power 1. Why power 1? Because 1 here. And I minus power 1. Okay? So now all these three, I must put the H plus here. So all these three are reagents. Okay, so now this becomes the rate law now. Okay, so 1, 1, 1. So here be 1, 1, and 1. Now if third step here is the slowest, put blue color. Okay, blue color here. Third step here. Okay, slowest step. This is again. I repeat. It's called a rate. What? Determining step. Okay, faster. So if this is the case here, these three fellows here will be involved in your rate law. Okay, HOI power 1, H plus power 1, H. Okay, now these two are a reactants. H plus and I minus. See, it's a reactant, so you don't care. But the only fellows who's the intermediate is your HOI. So where did HOI come from? HOI come from here. It came from your IO minus and H plus. So I got change first to OI minus 1 power 1 here, plus 1 here, H plus power 1 here. But H plus is a reagent, but IO minus is not a reagent. Where did it come from? From first step. Okay, which contains these two fellows here. So I'm going to change it again to H here, power 1 here, and I minus power 1 here. Yeah. So now all these fellows in this step here are reactants. So to sum it up, this is H2O2 power 1, or power 1 here, I minus 1 here, the 2 is not. So I minus 2, H2 here, so it's 1, 2, 2. Okay, so it's 1, 2, 2. Okay, right now you can see the answer here. This is 0, 8. Just show you 0, 8. Okay. Time. Now I'm going to take a bit longer. Okay, otherwise we cannot finish. Okay, see now. Okay, 1, 1, 0, 1, 1, 1, 1, 2, 2. Okay, see now. Okay, the marks here, 3 marks maximum. All right, right. Now let's do 2 more. I got what 10 more minutes. Okay, 71. Quite interesting, isn't it? 71. Okay, 71. Okay. Now this is the rate law. Okay. We have told me earlier. Right now there are two reactants here. Your ruthenium thing and then your carbon monoxide. This is power 0 because there's nothing here. So it's only first order respect to your ruthenium thing here. So they ask you now. There are 3 possible mechanisms for this reaction, which are described here. Okay. The first one, the slow step. Okay. Involve both of them. These are both reagents. Okay. The second one is involved with only the ruthenium complex. Next one is the ruthenium. So here, now this is a slow step. Give you straight away. This one give you this part here. All right. This is okay. All right here, and then the fast step here. Where see, this one is the product, but this is the intermediate. Yeah. This 1 step. This 2 steps. Right. This is 2 steps, but this is intermediate. Okay, so, well, which is the one? Must be there. Why? Why? Because, why mechanism 2? Because carbon monoxide is not in the rate law. See not? The answer is this. Right? Carbon monoxide is not in the rate law. That's what the answer is. Let me show you the answer, okay? It is 12, 12, no, 12. I say, time is not for us. Okay, yeah. all this ready, but I didn't have time to go through all of them. Okay, so never mind. Okay, I think it's on here. Okay, see now. Okay, right? Consistent. All right, because, well, it's not here. I don't know where is it. Okay, doesn't matter, right? The idea is because it's not in the, it's not, okay? Oh, good night, where is it? Okay, right? Because see, if this is the correct one, that means that CO will be in the red laws, okay, the red equation. So it's not. Next one here. Okay, 5 more minutes. Okay, let's do another one. 73. The time to go through all this. 73. 72, 73. Now, okay, that's why it's tricky. Okay, now for this reaction here, okay, see now, so I came up in my example here, hydrogen plus NO, okay, it's on here. Now these two are the reagents, okay, hydrogen monoxide and H2, and they found that the red law is on here, okay, not 2 here, but it's only 1 here, okay, 2 here, okay, right? You can see how I work it out here, okay, for the K, okay, I won't go through it because there's no time. So they say now here, the following mechanism has been put forward. The first step, of course, is NO plus NO give you N2O plus O. H2 plus O give you H2O, and H2 plus your N2O give you something here. Okay? If you add them up, it should give you the whole thing. Okay? Later. Remember, this is this one here. If you add up, it's very simple. All right? And this one cancel off now. Okay? Right? Here, the O cancel off here. Okay? Right? So what you left is 2NO plus 2H2, which is correct, U, and 2 plus 2H2, okay, which is actually the overall equation here. See? Okay, that's why this mechanism is correct. So now which if this is so, right? Okay, so actually this one here is the answer for this one here. So now they ask you, well, the first mechanism put forward, okay, suggest which of the 3 terms is the rate determining step. And explain the answer. Okay, that means that the rate determining step must have these 3 further steps. That means these 3 further play an important part. Remember, 2 plus 1 is 3. That means it cannot be the first step. Cannot be the first step. Okay, so if this is the case here, then I remember NO is not, okay, right? Now that means it can't be a step. So I must think, well, which is the correct step? Which is the one here? Okay. So remember, all I need to do is, of course, so you need to guess that. Okay, right? Okay. So I guess that step 3 is the slowest because step 2 I cannot go backwards to give you my NO. So step 3 can. So if step 3 is the slowest, I have to guess it out. Okay. So you got to guess. So if step 3 is the slowest, I get what? Rate equals to K and N2O. Where's N2? Here, sorry. N2O power 1, H2 power 1. Okay. So now equals to this. Now H2 is a reagent, N2O is not a reagent. So where do you get my N2O from here? So reverse back, I get NO and NO. Okay. Right now, see? Right, so now all are my reagents. So it's equals to K and 2. Now, so this is consistent with my rate law. See now, so this must be the slower step. See, okay, so it's consistent, right? All right, next one here, last 75, 77, last one, and we can go off already. Okay. Now here again, this is the one that I showed you just now. Okay. Now this is the rate law. Remember? In this reaction here, right, your chromium hexacarbonyl plus your P aldehyde, don't care what it's, okay, 1:1 is it? These are reagents here. Well, they say that, well, the rate law is this one here, which we determined earlier, okay? It means does not depend on that CO is 0, okay? Okay, that means, well, this one is true, but it's fast. See now, this is slow. That means if this is correct, that means the rate is equal to what? K CR CO 6 power 1 and PR3 power 1 because it's slow step. Okay, so this becomes the elementary step. This will become your rate determining step. That means these two will control the rate. But it's wrong. The rate determining step is just on your chromium hexacarbonyl. Okay, does not depend on your PR3. Here not. So the second one, of course, is this one here. Okay, becomes here slow step. Can also this one. Okay, it means this follow. This is the slow step. That means it's the rate determining step. That means if this is the case here, rate is equal to what? K, which is correct. CO6 power 1. See now? Okay, this is correct. Okay, now this is kind of transitional state, right? So this is a one step. It means that this one here is a slow step. Okay, because this two, that means this two will be in your rate determining step, just like this one here. Okay, this one is slow step, same again. This one is still same as this one here. So this is that means B is the answer. Now this is the answer here to give you here. B, mechanism is B. Okay, the mechanism is B. Okay, see mechanism is B consistent because it's the only mechanism that does not involve a PR3, just like it doesn't involve this carbon monoxide. Okay, in the rate determining step. See, only this one is there. Okay, therefore the concentration of PR3 does not affect the rate. Answer? Okay, so we have finished this one here, except for what is this? The lock and key thing. Okay, right. So this is a mechanism. Go over and see what I said. Go over again, so probably you can understand better. Okay, stop sharing. And